The new stuff. We actually learned Hooke's law in grade 11, but just really briefly talking about springs. You hardly touch on it. It's just like a multiple choice question. Now, springs actually, some of the same stuff, and then we make it harder, of course, is a pretty big thing in this course, and it's not that it's overwhelmingly important, but it does help us understand. It gives us a new energy to work with and a new way to tackle hard problems. So here's Hooke's law. I like, the term proportional, I think, is an important one to have a good understanding of leaving high school physics. The idea that a proportional means exactly this. So it says the extension of a spring is directly proportional to the force applied to it, meaning that if you have extension or stretch of a spring on one axis and force on the other, you get a straight line. That means directly proportional. And so this guy, Robert Hooke, sort of came up with this relationship. And he came up with the equation that F, I'm using X for spring force in this, because there's so many. It could be called elastic force, it could be called like spring, well that's S, which is Fs, which is static friction. Elastic is E, which could be confused with electric force, so I decided to call it X. I think that, the textbook that I often refer to might call it E or something. Anyway. Who knows? We're calling it Fx for spring force, and that's because we use X to denote the amount of stretch. And like I said, this is not new. Okay, so there's this idea that if you figure out the slope of this graph, that gives you a measure of stiffness of the spring. A more like a higher K, a higher slope would be a stiffer spring. So anyways, here's the equation for Hooke's law. And I think that you might find when you get to university that you do a lot more with Hooke's law. Like we don't touch on it very much in the forces unit of grade 12 physics. We deal with it mostly in energy. And so it is negative. Fx equals negative k times x. And the reason is you have to think of x and force as vectors, where like if you're stretching the spring in one direction, call that the positive direction, well then the force has to be in the negative direction because it wants to pull it back to its equal spot, and that's why. But I don't want to dwell on that in this course because we're using this equation related to energy, and energy is scalar, so we're not going to worry so much about the negative. So from a practical point of view, I think I mean specifically in this course. In this course, the fact that it's negative, if you don't feel like you really get that, it just doesn't really matter to me because it doesn't matter because we're not going to deal with spring force so much as we are spring energy. Okay, so don't worry about that too much. Just get the idea that spring force is some constant, which is a measure of the strength of the spring. You could have, by the way, a spring constant on an elastic band. It's sort of anything that's stretchy. You could figure out the amount of stretch. So a really thick, strong elastic band would have a K value that's a bigger number, and a really loosey-goosey elastic band would have a low one. Okay, so what's this K again? So yeah, I said it's a measure of stiffness, and I told you this already. The units for K are newtons per meter. That's really just because, right here, it makes sense because it tells us how much force is required to stretch or compress a spring by 1 meter. So if you wanted to stretch a spring by 1 meter and it took you 10 newtons to do it, then the spring constant is 10 newtons per meter. Okay? Pretty easy. All right, so we need to really get a good feel for springs in this course. We are getting into the much more detailed in grade 12 compared to grade 11. So say I have I'm going to call this one a horizontal spring. And say there's 3 sort of pictures here. This indicates that the spring is stretched by 10 centimeters. I'm making up numbers. The numbers mean nothing, right? It's just the idea of it, right? This number doesn't, though. From its equilibrium position. An equilibrium position on a spring is where it's not stretched at all, where it just wants to sit, right? And then often, not always, but often you could compress a spring as well, right? So both of these have x values of 10 centimeters, but we put it in meters, so 0.1 meters. This one doesn't, though. This one is 0 because it's in its happy place. Okay? So either one of these, you say the x is 0.1. And like I say, when dealing with forces, we might, if we decided to call right positive, then x is positive 0.1 here and negative 0.1 here. Okay, but like I said earlier, that since we're dealing with scalars, it doesn't really matter. Just call it positive or negative. everything is awesome, like the Lego movie. Okay, so that's just what the parts of a spring or what it looks like. We deal a lot with vertical springs in this course too, and there's a few different things to consider here. Okay, you've got there's your equilibrium, where just a quick thing you have to get your head around. We never assume that a spring itself has mass. Of course it does. It does complicate things incredibly, and that's why I'll leave that to some, if ever you have to deal with springs in university, we don't deal with that in high school. We just assume always that you got some spring that has no mass compared to whatever mass you hang off of it. Okay? So a vertical spring, though, the interesting thing is it has two equilibriums, right? One is the equilibrium position as if it wasn't stretched at all, if it was sitting horizontally where it would be, right? At x equals 0. However, if you had a spring and you sort of let it come to a rest on a vertical, like it's a vertical spring, and you let it just rest, you let go of it gently, it would have what we call a stretched equilibrium. Okay, again, these numbers are just numbers I've made up, 10 and 20, right? So in this example, or in this picture here, I'm saying, okay, you've got, excuse me, you've got the equilibrium position, you've got the stretched equilibrium, and then this would be, say it's just let go and it's falling towards its stretched equilibrium. But if it did fall, eventually it wouldn't just stop at the stretched equilibrium. It would keep going and it would bounce up and down, and then because most springs are not ideal, they will eventually come to a stop, right? They'll eventually stop, and where it would stop would be the stretched equilibrium. Okay. This is called the stretched equilibrium, and we call it a stretched equilibrium excess. Okay, so in this case, I called that 20 centimeters. Yeah. So here's my bonus question for you, and we'll have clickers tomorrow in class, or maybe the next day in class, and I go through sort of how do you figure out where the maximum speed of a vertical spring would occur. So in other words, you're holding a spring, you hold it here, say, you let go of it. Where does it end up going? Where's the maximum speed? You let it go to its equilibrium position, or its stretched equilibrium, and it bounces back and forth for a while. Where's it going the very fastest? And I'll leave you to think about that. If you can give me the where and with a good justification, then I'll give you a bonus. Okay? Okay, so let's do some examples with Hooke's law. So here we have, notice the term, ideal spring. We always assume it's ideal, but ideal just means that there's no friction, and that if you get it moving, it would just keep moving back and forth forever. There would be it would never come to a stop. Okay? Every spring has friction in it, and so they're not really ideal, but that's a great thing about being in high school. You get to assume things are ideal. Okay. Anyway, so we have a spring. We know it's spring constant. We want to find the force. Okay, the force the spring would exert on you if you stretched it north from its equilibrium position a distance of 16 centimeters. So here it's happy place. I stretch it. So what's the spring force? So you just take the spring constant times x, kx, right? Hooke's law. And then forgetting the negative and all that, let's just say, what's the direction? The negative refers to direction anyways. The direction this force would be on you would be in the south direction, right? It'd be, like if it's sitting here, the spring wants to come back to its happy place, so it's pulling south. Okay? And part B, determine the force you would have to exert on the spring to compress it south. So this means that I've pushed it, I don't think I've got a picture, no. I push it in 16 centimeters this way. Well, now it'd be the same magnitude because it's still 25 times 0.16, but what's it saying? I'm misreading the question. Oh, determine the force you would have to exert on the spring. So this isn't the spring force. This is what you would have to compress it. So if I want to compress this spring over here, I've got to apply a south force as well. That's a tricky one. That's looking at the wording of the question. Okay, another Hooke's law question. Easy. We did this last year. Determine the force constant of an ideal spring that stretches 1.5 meters. Okay, when you have that much force, it's simply the spring constant, simply force divided by stretch. making sure you're in meters and newtons. And I know that's a good answer for a couple reasons. One, the numbers make sense. Plus, generally, our R in this class, spring constants typically end up between 10 and 100. That's not a rule. It doesn't have to be that way. However, it does typically, I know that that's a normal number. Okay? Okay, vertical spring. So this tells me the unstretched length is 30 centimeters. That's just hanging there, right? I put a kilogram mass on it, and now it's out to 48 centimeters. And I want to find the force constant, the K value. Okay, so I know the mass hung off it. Remember, I'm not including the mass of the spring. I know the stretch. So the X is how much it's stretched, and that's why I think this question is good. It's not 30 or 48. It's the difference between the two. It's unstretched, right? How far it's moved from 30 to 48. So that's why it's 18. And I'm just looking for K. Well, I guess something you have to know is that the force being applied to this is the force of gravity. The reason it's stretching is because of mg. So that's really my Fx. Okay? My force applied to it is 9.8 newtons, mg. So then I just sub in, and again, 54, like I say, typical numbers between 10 and 100, so that's a good number. Okay? So this is important to know then. Don't forget this. If it's a vertical spring and you want to find the force applied to it, the force applied will be the mass that's hanging off of it times 9.8. That's all. Okay, the fishy. This is the last example. Okay, so here I've got this fish, and it's hung off. This one's a harder question. A fish, and it's hung off a vertical spring. So here's my vertical spring. I got my fishy hanging off the end, and I know the K value. So there goes my 10 to 100, right? And show you an example right away that's different. So there's my K value. And I want to say, how much does the spring stretch if it stretches slowly? So all I'm saying is I'm not dropping it or throwing it. I'm just sort of letting it fall. What's this going to be? What's my stretched equilibrium? That's what I'm asking you. And I call it a new equilibrium, or XS. Okay? So if I look at the fishy, I can say, well, again, at the stretched equilibrium, it's sitting there, so the up force must equal the down force. It's got no net force on it. The up force would be spring, and the down will be gravity, so you equate the two. Right? So K times the stretched equilibrium equals mg. Just turn around and solve. Not very much. So that fishy doesn't make it stretch very much. However, in my mind, that does make sense because that's a huge spring constant. That's a very stiff spring. So our how much is our fishy weigh? Our 1.37 kilogram fishy won't cause it to stretch very much. Okay. Part B says, if the fish is attached to the unstretched spring and allowed to fall, what is the net force on the fish when it's fallen 1.59 centimeters? So it's put on here, right here, and it just starts to drop. And so somewhere in the middle here at 1.59 centimeters, I want to know the net force on the fishy. Okay? So just scrolling ahead here, pause if you need to, but I'm going to scroll ahead. So I'm going to say, let's call down positive. And this is a force question, not an energy question, right? Things I know the mass, I know the K, I know the X value, and I want to find the net force. Well, now the fishy's it's moving, so there is a net force. Well, motion doesn't mean there's a net force, but we can't assume there's no acceleration. So we're saying let's assume there's a net force. It's going to be gravity minus Fx, right? And so you just sub in the numbers. mg minus kx. We know the x value, we know m, we know k, and you end up with 5.2 newtons. Okay, so that's the net force. And just be careful because I figure the thing's moving downwards, I decided to call down positive. So my net force is whatever's pulling it down, which is gravity, take away whatever's holding it back. Okay? So I don't know, the number looks pretty good. Say good work, Miss Stone. Check mark on it. All right, one more. It's saying let's find the acceleration. What's the acceleration of the fishy when he's right here? So we know the net force is down, and this is just straightforward Newton's second law. I know it's a good answer because it was higher than 9.8. I'd have to be concerned. but it's not, because it's fall in free fall. Well, it's not in free fall because there's a spring holding it back, so it makes sense it's something less than 9.8. And that's it. Okay, so that's the first little bit of Hooke's law. In the next video, tomorrow night's homework, we'll be looking at elastic energy and spring energy. Okay, so that's it. Let's go to bed.